We are going to discuss like statistical inference from cosmological signal. Of course, we are talking about the H1 signal here. Now, as you remember from like last two lectures, that there is no concrete detection or measurements from global signal side. So we will consider interferometric observation here, right? So this figure, like I described, that okay, there are many telescopes, in radio interferometer, LOFAR, ARTFAR, NENOFAR, SK will come soon. MWA, HERA, those are observing, and they are probing different frequency band or redshift band. They have their own different configurations, antenna design, antenna distribution, etc., which give them unique advantages, also disadvantages. And we discussed that, we didn't discuss, but this will be discussed in detail hopefully soon, that problem with this probe is that the signal which we try to simulate, this is very weak. So the signal, your signal, this is of the order of 10, 5 millikelvin level. While this photon, which has been emitted in 1420 megahertz, these will be propagating to us. In this process, their frequency will go down, they will be redshifted. But when we'll measure, we'll basically choose a frequency band. Our observation doesn't care whether that particular frequency, which it is measuring something, radiation has been emitted from other sources or not. So what will be measured is that, for example, if you are observing at 120 megahertz, all sources of radiations which are coming to the telescope at that frequency will be measured. Among the additional terms to this 21 centimeter signal, there are foregrounds from our galaxy, from extra galaxy sources. There are noise from the Earth. There are RFIs. There may be instrumental effects and lots of complicacy, which is a usual context of radio astronomy. The major problem for your 21 centimeter signal is that is very weak compared to like local galaxy which emits in 21 centimeter signal. But nevertheless, if data analysis pipeline has accurately, let's say, subtracted or dealt with the foregrounds, and they have more or less, they have a calibration method which is working perfectly, then it is possible that from a map which contains all the information, all different radiations, which is several orders of magnitude larger compared to the AR signal, it's actually possible to recover the signal which we are looking for. And that's what several teams are trying in last several decades. And here we stand. I have already explained this figure, that these are the upper limits at certain K value. Means like the power spectrum will be somewhat below this value. So in this particular hands-on session, what we will do, we will use one of the ones of such measurements, which comes from Martin's 2020 paper, based on 10 nights LOFAR observations, and they put these upper limits as function of K, right? So what we want to see, whether any reionization scenarios can be ruled out, or if we can actually constrain our source model, so to say. Now, for this talk, we will be mostly concentrating on source properties, means like how many sources has contributed, what are their emissivity, and we will be using the same model which we were describing. So that is based on this set of approach which I described, based on 1D radio transfer. For that, we didn't use that simplified version, but we use Grizzly code, which source model is slightly different, but still it will produce power spectrum following this same technique that it will use n-body simulation output. You use a post-processing method based on 1D ray transfer and putting ionized regions and heated regions isotropically around the sources, which will eventually produce a map. So what is done that we explore the parameter space, zeta, a mean, and this one minus T gamma by Ts, and we produce many power spectrum corresponding to different possible realignment scenarios. Now what you see that these red points are the upper limits from loafer. This is 1 sigma level of error bar. Certain scenarios has power spectra, which for example here, which lies above these points. So these points are telling that power spectrum will be somewhat below this value. This cannot be above this value. If these are above, so these models are basically ruled out in 1 sigma level at least. But from here, it's not like a probabilistic way. So measurement wise, you see that there is a mean and there is an error bar. So they are also not certain where to put actually the upper limit. So there is a probability that this number can be here or slightly upper, but with a probabilistic way. That is the error bar, what it is saying. This, what we find that a patchy type of realization models are actually ruled out. For example, this map which you see, this is this uniform spin temperature map, the exact model which we were running in our last lecture. And this is creating ionized region. These are ionized regions, and these are regions, neutral regions, but no heating has done. Very big ionized regions are basically occupying the entire interactive medium. This particular patchiness will create a fluctuation which will give a power spectrum which is shown in this dashed bold line. So this is one of the scenario which will be then ruled out. This is not the probable scenario at adhesive 9, which is saying. But what we want to do is in a probabilistic way, we want to see if we can put constants on our parameters, and okay, this is the wrong set of parameters, but you get this idea that now what we will use, instead of Grizzly, we will use an emulator, which basically also gives power spectrum. Why we are doing that? Because from last exercise, you see that, okay, even for a set of parameter, it is taking maybe 1 minute to produce the power spectra. If you want to do in a Bayesian way, have a question?
So you're saying that the patchy model is ruled out, but here we are considering fluctuations due to the varying matter field, right? And what we expect is that there will be an additional fluctuation due to this spin temperature as well. So if we are considering a uniform spin temperature, then if the patchy models are ruled out, like all of them are ruled out or some of them?
It's not like the patchy reaction models are ruled out. This model is ruled out. So this model is like, okay, universe is not heated at all, and bubbles are quite large in characteristic size wise. This is a particular scenario. So they in patchy reaction model, so you can now change the 1 minus T gamma by Ts factor. Let's say if you make Ts much larger than TCMB, your this power spectrum will come down to here. So this is a valid model. Patchy reionization, but heated. This is a still valid scenario. But this type of ionization region distribution with no extra heating, that will not be the scenario at SU 9.
And what is the rest?
This is RECIF 9. So we like, okay, this is our fiducial RECIF. We will only consider one RECIF. We considered that RECIF also in our previous lecture, yes. This is like 2.7 Kelvin or something. Simplified delta TB equation, yes. fluctuation will, true. The equation that will enhance the fluctuation a little bit, right? Ulta. Yeah, I mean, there are several things going wrong in this particular modeling. So we didn't consider reciprocity distortion, which will boost actually a little bit of this type of signal. Maybe like, okay, counter argument wise. Right. So to say, like now you see the inference, particularly this is highly dependent on what type of model has been used. Because you change your model, source model, your power spectra probably will differ. That is why, like one philosophy people are now taking or considering is that instead of source model, you look for the characteristic properties of the ionized regions here, which I was talking about, this image-based statistics. You basically characterize the ionization regions based on some statistical method and try to infer, do a Bayesian inference on interactive medium properties instead of source properties. But here anyway, like I say, for demonstration, we will only consider source property and source parameters. So one thing to realize that these are not measurement. One measurement will say that, okay, you have a mean and an error. So you need to find a model which will, let's say, fit best. This is what you will try to do, but this is an upper limit. So likelihood has to be written in a very different way. So for a measurement, for example, if this is a measurement, a model, if it is lying somewhere here, this is very unlikely the scenario. Also, this is true for a model which is lying quite far from this point. But in the upper limit scenario, this model is unlikely model, but these are valid models. So this way, for an upper limit, your likelihood has to be modified. And taking into account that this is the upper limit, a likelihood can be written in this way. So I'll just simplify what it means. It means that if a model is lying quite above these upper limits, at least at one Kelvin, you will have an exclusion likelihood going to 1. For other type of models which lies below these points, your exclusion likelihood will be of the order 0. So this is a error function dependence, where basically a model which lies quite far from these points below, they will be very much valid models. Now, using this likelihood, now we can explore a Bayesian type of analysis, which will produce features like this. Now, this is a plot which we want to actually reproduce in this particular lecture. Before that, let me just explain what it means. As we have seen from our previous exercise that increasing zeta was increasing the ionization fraction, right? With increasing ionization fraction, the patchiness was also increasing and the amplitude of the power spectrum also increasing. So that is why it was preferring larger value of zeta. For this analysis particularly, we also included CMB constants, which exclude a quite large volume of our parameter space. One thing I should clarify here is the inference which we are doing is not on the valid model, but on the excluded model. The thing is, you see that all these models are valid, which will, if you explore, like mostly like your entire parameter space will be valid, and only small part will be excluded. It's not a very good statistic in that sense. So that is why we did it in an opposite way, that we will do a statistics on these models. Right? what are their nature, what are the source parameter corresponding to these models, etc. And that is the approach which we took. Right, and what we found is that Liaison scenarios model, which are led by zeta value, let's say around 100, and m mean value, let's say around 5 into 10 to the power 10, and 1 minus t gamma by ts model around minus 12, they will produce Liaison scenarios which will have quite high pass vector value at large scales and thus ruled out. So this is a probabilistic way, of course. Bayesian analysis, always you have to keep in mind that these contours, for example, doesn't mean that these are excluded scenarios, but it says that they have high probability to be excluded. Right? Significance of this exclusion, that has a different measure. Anyway, so the task for this tutorial will be now use the code which we basically provided and explain a little bit the code and run it and try to reproduce this particular figure, which is, let's say, which will be the constant using this upper limit, this one, which will be the constants on zeta m mean and this 1 minus t gamma by ts, this factor, but that constant will be only on the ruled out model, right? Any questions on this part? I don't have any other slides. So now it will be only like demonstration. If you have any question, concern about the scenarios or likelihood, etc. Yes, so likelihood is this one. This assume that the error bar on this likelihood is more or less a Gaussian type of nature. If that is the case, then you can find the probability of exclusion of a model for one side and also for the other side. So what finally it will give is a error function type of likelihood. It's like the functional form, if I try to plot it. This will be 1 and 0. So now it depends on like how far your model lies from the mean of the power spectra. You will have a value something like this. If it, let's say, lies somewhere here, you will have a exclusion likelihood, which is, let's say, 0.1 or something. If it lies just above the mid, it will have a likelihood, let's say, 0.8 or something. If it lies quite above, then it will approach to 1 in that way. Is the error bar in upper limit, which says that, okay, there is uncertainty of the measurement. It doesn't know, it is associated with some error. Mohit?
Yeah, for inference, make sure you are in the inference conda environment. So to check that, you'll see inference before your user ID. And then inside the main directory, you just write Jupyter lab. So you will see this inside the directory, go to inference, and there is a script file. Open that and make sure right side Here the kernel shows inference or Python 2. Yeah, so make sure that your kernel is either shows inference or Python 2. That's it. And then you can, it will work, yes.
I mean, the part of the codes are like that. First, we are loading this. I'm just explaining. We are loading this GPR model ps.scv. This is the emulator, which we basically pass our source parameter, and that will produce power spectra at 3 kelvins, which we will use. At a later part, we are reading this ps final result.txt, which has the upper limits from LOFAR, right? And we are reading 1 sigma error and the mean value of this upper limit results. Then we are defining our likelihood, and for that several functions had been written. And the likelihood is actually like the equation which I was showing, that likelihood depends on the mean value of the upper limit as well as the predicted power spectra from this emulator and the error bar on this upper limit. So we changed the error bar a little bit. We added 10% modeling error from our side, because like as you know that this power spectra estimation, these are dependent on what type of source model you use, and there are inaccuracies. This is one data transfer based code which has like 10% error if you compare to 3D data transfer codes. So that's why like, okay, there is uncertainty from the predictions of power spectrum as well. So we added 10% error totally. If you scroll down a little bit, Yash, then this is the log likelihood, which is defined in this way. A prior has been set on zeta value, which is a little bit, or m mean value. So what we found that in this parameter space, so there was a little bit limitation of this emulator. What will happen is that zeta and m mean so at this corner particularly, when you will have high zeta value and low m mean value, then it's highly likely that you will have a total ionized scenario. That particular scenario will produce a power spectra which is quite low. Right? So to avoid this scenario and to include constant from CMB, we have basically excluded this certain part of this two-dimensional parameter space. That is done by putting a prior on this Ilian likelihood. So there is the second line, which is doing that. And then we are predicting the log model, which is using the emulator. And then we are finally estimating log likelihood for a given set of parameters. These things are later coupled to EMCE, right? You know how EMCE works. You have to choose a number of workers. Our dimension, parameter dimension is 3. We are using 10 workers. So that to say, like to start with, it will randomly put, let's say, 10 points. We also have to give a guess point for this analysis, which has been given in this in 12 thing, right? We have put a guess initial points of 2, 10.6, and minus 12. And we are running for 5 into 10 to the 4, this number of iterations. So once like a likelihood has been estimated, it will choose its next point based on the algorithm. And finally, it will basically produce this chain which contain all different input parameter set which it has used. And the particular MCMC technique suggests that if you now use the entire chosen parameter set and make a statistics, that will basically give you the probability of exclusion. And that is what has been shown here. So after this 5 into 10 to the power 4 iteration, we are seeing that there is a high exclusion probability for a large value of zeta and larger value of M min. So what is happening in this particular scenario is that, so you have a realization scenario which is preferring a large zeta and large M min, and it is saying that the real scenarios driven by these type of parameters will be, will have more probability to be ruled out. So large M min mean now in my box there are only few dark matter halos, right? And large zeta value is saying that although there are few sources, but around the sources the ionization regions will be quite large. So this is very much Prachi reionization. It also prefer a value of 1 minus T gamma by Ts to be highly negative. So that will increase the contrast between this ionized region and the neutral region, which will eventually, like if even for a Ts much larger than T gamma, this scenario, the power spectra for this type of model will have quite large amplitude at large scales. If you assume, so this is Ts much larger than T gamma, but when let's say 1 minus T gamma by Ts is minus 12, and if I say it in a dotted curve, so the entire this curve will be shifted at all scales. It will be like boosted. So these type of scenarios will have high probability to be ruled out. Now from here, what we are learning is that 1 minus T gamma by Ts, a large value of smallest value in this particular parameter set, is saying that interactive medium, which is neutral, that have to be unheated. This will be like cold, what we predict from cosmology. And this M min and zeta combination is saying that reionization has to be very much passive. So this is a like scenario which we can conclude has the largest probability to be ruled out. Okay. Any questions regarding the interpretation of these results? Are you able to run this code on your laptop? It's running, right? Okay. Okay, good. I think, okay, you have a question? Last plot is not working. Okay, last plot is a convergence test plot. This plot is working? Yeah, last plot, I don't know. It was working for some people, it was not working for others. Maybe, okay, this is the convergence plot which I had kept there. If that is not working, this is fine. So this is a usual practice, like when you do Bayesian analysis, then you have to check for convergence. So there is a tau estimate, which will eventually, when you increase your iteration, it will go and saturate. You need to check that one. Otherwise, like we have used 5 into 10 to the 4 iterations here. You can do this analysis for 100,000. You will get some statistics, but whether that is reliable or not, that you cannot tell until you see that, okay, your chains are converging or not. Yes. I don't know, like it is visible here or not. Maybe it also doesn't work here. Yeah, it also didn't work in this laptop. Yeah, I don't know. It was working on my laptop. It worked for some other people's laptop, but yeah. But I mean, this convergence test criteria, these are my standard EMC website. You will find the code, how to check the convergence, etc., etc. So yeah, that's fine. Okay, if there are any other question, concerns, yes.
If I include this spatial fluctuations in TS, then how much a change in the power spectrum would I expect?
So there is a completely different set of model which we can rule out, which will be, let's say here I am talking about that we need a patchy reionization and cold interactive medium. What we can show, if we go and check what is the ionization fractions of this type of model, we will find those will be around 50%, 50% ionization. Okay. Another set of model which we can found, if you include spin temperature fluctuation into your simulation, which will be, let's say, neutral, completely almost neutral medium at recipe 9, which is a completely valid scenario, and spin temperature fluctuation models. The beauty is that here the fluctuation levels are, let's say, this is 0 millikelvin, and this is, let's say, minus 200 millikelvin. For a spin temperature dominated type of model, what we will find, these regions are now my positive region, that will be, let's say, plus 20 millikelvin, and it remains, let's say, unheated. So this is 200 millikelvin. So contrast is actually more when you are considering spin temperature fluctuation models. So I am not showing those scenarios here because this is a demonstration and I just wanted to keep it simple. But yeah, in principle, like you have to consider all possible scenarios, including spin temperature fluctuation, ionization fluctuations, and put constant on your model. And yes.
So
Yes.
So the second one, it
Hmm.
is there is a peak, and from there you are calculating the value. It can be mean or something like that.
Hmm.
But in case of first one,
Hmm.
how the parameter is coming, like
Yes. So in all Bayesian analysis, if your contours are not close, your limits, for example, like the numbers at the top, those are highly dependent on your choice of priors, which are the ranges of your parameters you are choosing. For example, you could have extended your zeta parameter to 3, 4 or something. Your limit on those parameters, 1 sigma, 2 sigma limits, which it is showing, that will be changed.
is there any restriction in the parameter space for that parameter?
So the value of zeta, for example, like as we don't have very clear understanding about the emissivity of, let's say, the source, how bright those could be. So that is why, okay, we generally choose a range for those parameters, which is particularly ad hoc. This doesn't have much of, let's say, physical background. Here, for example, the M mean, that particular range has been chosen from, which is limited from our n-body simulation. M-body, in a better sense, like one could have included small mass dark matter halos. We are only including dark matter halos about 10 to the 9. But in principle, there could be dark matter halos which has mass 10 to the 8, even below that. So your posterior distributions will actually get modified with that. So again, I am repeating the results from the Bayesian things. You have to always keep in mind, those are highly dependent on priors. Whenever like we are showing these numbers, we have to keep in mind that these numbers has arrived based on the x-axis, let's say, or the range of parameters which we have chosen for our analysis.
For example, for the first case,
Ah.
from that distribution, how you are calculating the value to be 1.8 plus minus something?
Okay, so this is a mean value 1.8, like from the distribution, which you can, and this 1 sigma level wise, it says like, okay, the parameter range, let's say, which contains 68% of your data. Something like that. So it's like 2 sigma level and 95% of your points are within that range.
And also, if the distribution is something like that, so like
nearby to some, let's say, range. It is not like
you are
jumping.
not using any convergent test or
There are convergent tests. Okay, the plot is not working, but we have done a simple convergent test. For a good MCMC analysis, what you need to do, you have to first of all increase the number of iteration. We are using for a demonstration purpose because we have limited time. We should have like ended this MCMC run within, let's say, 10 minutes or so. That's why we have reduced the iteration, but for a, I mean,
if you increase the number of iteration for example, this case, the curve, the histogram will be smooth, not the distribution will not change, right?
Distribution will not change.
So
if it is more or less, it is going towards the convergence criteria, the distribution will be the same. Let's say here already convergence criteria has reached, and you are now increasing the iteration, these PDFs will be seen.
oh, thank you.
So, when Raghu is talking about convergence criteria, do everybody understand what is convergence in MCMC? Everybody understands it, so no need to have clarification. Okay, perfect. Oh, okay, fine. So it is very simple, right? These are random walks. So random walkers have walked in the parameter space, but that's only one random walker. So you need to have multiple random walkers. These random walkers should converge in the most probable region of the parameter space. That is convergence test. One of the popular convergence test is Gelman-Rubin convergence test, and that is what Raghu is performing right down there. So you run multiple random walkers and they end up in the same region of the parameter space. And the error bars also are total number of steps more or less in what is called post-Barnine region and what is there in the 68% region. That's how the error bars are calculated here.
So during this MCMC type of analysis, two things need to be handled very carefully. So for example, here we are using 10 workers. I can choose this worker in a very small region. Say I don't want a long run and I know that, okay, this is the parameter space which it should converge. And I just say that, okay, you put 10 workers just nearby to that point. It's a very wrong way to do it. In a good way to do it, that, okay, you basically sample that workers randomly in entire parameter space. And second thing is that you have to let it off very far away so that it can explore the entire parameter space. Otherwise, what will happen, let's say I choose a worker in a very confined zone, and let's say there is a local minima. It's not a good solution, it's a tentative solution which is giving some likelihood, okay, but this is not the maximum likelihood. It will just go and convert there, which will give us very wrong result. What we will have to do that, okay, you have to let this basically exploration all over the parameter space, and there are few parameters to set for that in EMC or Cobaya or any type of Bayesian inference that need to be considered carefully. Any other questions?
Yeah. So if you want to see this convergence for whoever it's not working, in this line you change the text use tag to false. So you there in your file it should be true, change it to false. Yeah. And remove all the labels here. So if you remove the labels and here also change this also, then it should be working for you here. It should work for you.
A LaTeX plugin, nothing
Yes.
else.
So
Okay, there is nothing else to discuss from my side. If you have any question, then we continue. Otherwise, we will break for, let's say, 10 minutes and come back. And that will be like another hands-on session. Ilian will basically giving demo on PyC array. So I don't see any hands. So let's break for 10 minutes.
Yeah. So we come back here at, let us say, 5:55. Okay. Oh, 4:55. Sorry. Yes. Yes. 4:55, please.